Okay, so for this this quiz, the quiz was given. You were given some information. You were given PI information, which everybody just walked right over the top of. PI is your point of intersection, so you had to deal with that. You had a delta that was given of 15 degrees, 25 minutes, and 30 seconds, and you had a radius of 2,000 feet. So it asks you to calculate a deflection angle and a long chord to station 73 plus 75 sitting up at the PC. Okay, so almost everybody said that this was the PC, and there's no way that the PC is equal to the PI. Who can tell me why?
The PI would be the middle.
Well, kinda. It's the yeah, you're pretty close in your determination, but really, here's what I would look at in this picture. If this is my PC and this is my PT, PI is out here. So if you're saying middle, yeah, it's the bisector, but technically that's the middle of the curve. Okay, does everybody see what I'm getting at?
Yeah.
Okay. So I didn't necessarily disagree with what you said, but I just want you to understand that is at the point where the two tangents come together. Okay. So first off, everybody just assumed that this was this. Okay. It's not. So the first thing you had to do was calculate PC. Who can tell me how we do that? What's the distance from the PC to the PI called? Anybody know what that distance is called?
Is it the algebraic difference?
No, we're not talking about vertical curves here. Somebody else had a question or an answer? This is a horizontal curve. So this is called your tangent, T. So what you had to do first, and I think I had one person solve T. So T is very simply solved by the radius times the tangent of half of delta. So you've got half of delta tangent. What you get is 270.85. So now how do we solve the PC?
So if we calculated the tangent, that distance, we could subtract it from the PI, and that would give you the PC station location.
Absolutely. So we would take the PI station, which is 2755.10 minus T, and you get a PC station 69 plus 84 25. So I think like I said, only one person or maybe two people did that. So then you're sitting here at this point and you want to go to a station here. So what you need to do is calculate the long chord to that and the deflection angle. Okay, so now most of you guys use the right equations. You just use the wrong pieces of information. So what we need to do first is solve the distance from the PC to this stake here, which would be 7375. So we're going to call that length of arc. So what we're doing is taking 7375 minus the PC station. That gets us the length of arc that we want to solve to. So that gives me 390.75. So then how do we calculate the deflection angle? Most of you guys did this. Who can tell me the equation?
It'd be LDC over 200.
Correct. So This is the L we just calculated, okay? And then degree of curve is just your 57, 29, 578 divided by what?
The radius.
The radius, which is 2000. So what you get here is 5 degrees, 35, 49. Okay, so most of you use this equation, but you didn't use the right variables in it. Okay, so the last thing we then needed to do was calculate the long chord, which is 2 times the radius times the sine of the deflection angle, which is that angle. So it should be pretty close to L, just a little less, which it turns out to be that. Okay, so the big thing that people did is didn't recognize that this was what was given. So they didn't solve this, you didn't solve that, you didn't solve that, and then didn't get this correct either. So that was those were big issues, okay? Does everybody see what I'm getting at there?
Yep.
Okay, so we need to look at some of this stuff. This is exactly what we did out in the field. You know, we had deflection angles. Now I hadn't calculated them for you, but it's not very hard. Just got to recognize where you're sitting, where you're going. If you're starting at a PI, then you have to back off either to the PC or the PT kind of thing, okay? So you'll probably see something like this on a test. So, and if you do have any questions, don't hesitate to ask. Does anybody have any questions further on this problem before we move on?
No, that makes sense now.
Okay, perfect. All right, so let's migrate back over. Now we had finished last week. We did a lot on the board the other day, so I'm hoping that I took care of a lot of vertical curve issues for you. But we're going to go through some of this real quick. I think last week I went through this problem, didn't I? On the sample, does anybody recall vertical curves? We did this, I think, last week in lecture, and then we also did this stuff on the board for you guys that were there on Thursday. Anybody questions about how to calculate vertical curve? Rate of change of grade, equation of parabola? Any questions?
I'm good for now. I just gotta rewatch the lecture.
Okay. I mean, we've got time to go through something. Well, I'm definitely going to go through one thing here, but which probably will do a lot of that. So maybe this will review. So the one thing I don't think we got to talk about was this concept of high points, low points. Okay, so notice if you have a parabola that has changing grades, so in other words, if you go from a positive to a negative or a negative to a positive, you're going to get a high spot or a low spot that develops. So pinpointing exactly where that is and what the elevation of that is very critical, okay? So we're gonna look at this. The equation to solve where that high point or low point occurs is given by this equation here. You can either use that x is equal to negative g1 over r, or this guy, which is a little bit more cumbersome to use, G1L divided by G1 minus G2. These are exactly the same equations. This one's just a little bit easier to use. Okay, so we'll use this on an example to show you. So what that X value is going to be, it's going to be the distance from the VVC to the high point or low point. Okay, so let's look at, we've got this problem here, and what it shows me, I'm going to write this down. We're going to go over to my little whiteboard here, but I have a -3 grade coming in and a positive 1.25 grade going out. So that would be G1 and G2. We have a PVI station and a PVI elevation. So we're given 210, it looks like, and 8580. So what we're going to do is solve the location and the elevation. And notice it says that we have a low point there. So does everybody see what I'm getting at there? Another piece of information that's really critical on this guy is the length. So what is the length on this? Can you guys see that? Length right there?
Yeah.
Yeah, let me do this. It's a little, I think it'll be a little bit easier to see if we just go from that current slide. That's much better, isn't it? So we got 350 for the length. And we've got grade in, -3, grade out 125, and 210, and 8580. So let's take a look at doing this problem, and this will actually solve pretty much everything on a parabola that you would need to. So if we know how to do this, then we're pretty much going to be good to go. So there are some problems out of chapter 17 I did assign. So, you guys should be looking at that. So let's run through this, and then we'll get started into the new stuff today that we're going to get into for our lab. So I'm going to draw a quick sketch showing us what's going on with our parabola. So we have a grade down. All right. Maybe we do. What's going on here? Hold on a minute. It's always something with this thing. That's not working either. All right. Let's try that again now. Okay, so we got a grade down and a grade out. So it's a flatter grade going out than it is coming in. And we have this parabola that's we're doing a kind of like that, close enough. So we basically have a distance here of 350 feet. And so we need to know what the BVC station is in elevation. We really might as well just go ahead and get the EVC information, and then we'll be able to solve everything else that we need. Okay. We also know this guy is sitting at 85 plus 80, and the elevation is at 210. Okay, so who can tell me what we need to do first in order to solve this? So we need to solve BVC first, EVC second, equation of parabola, but we also will need R. So let's do the BVC. Who can tell me how we solve the BVC station? We need the station of this guy. No one knows how to do that? It's going to be the station of the PVI minus half of the distance back. So that's going to be 350 divided by 2. So what does that give us? Anybody get a number?
84115.
I got something slightly different. Let me check mine. I might have fat fingered it. So I get 175 minus 85, 80. Is that correct? I get 84 plus 0.5.
Yeah, that's right.
Okay, no problem. I just wanted to verify. Okay. All right, so we need to get the elevation. So the elevation would be the elevation of 210 minus a -3. Okay, because this is coming down at 3%, and this is going out. Why I'm subtracting a minus is because I'm actually going to add it, see? So the distance here is going to be the half of that distance. So what he said that was 175 feet. So I'm going to put that as 1.75 stations. So what I'm doing is percent grade times station will give me the rise in feet. So that's probably the hardest thing you deal with vertical curves. So I've got a rise here of 5.25 feet. So we're going to add that to the 210. So you guys checked my math, but it looks like this is sitting at 215.25. Anybody agree with that?
Yep.
So over here now we know that this is 84 plus 05 for an elevation of 215.25. Okay. So now we've got the EVC, and that's going to be equal to your PVI station plus half of the distance of L. So notice here I'm working in feet, okay? So sometimes you're working in feet and sometimes you're working in stations, but it's not that big of a deal. You just got to remember what's going on there. So this is 87 plus 55. That's what I'm coming up with. Anybody agree with that number?
Yeah, and if we were doing this problem and we didn't have that intersection point,
Yep.
we can just solve that ourselves by 350, and then we have that, and then add it from either EVC or BVC.
So are you saying that you don't have this as a given?
Yeah, if we didn't have that as a given.
Well, usually I'm going to tell you that you're almost always going to know this, okay?
Okay.
Because otherwise it would be really hard because you'd have to take this slope and intersect it with that slope, okay? So I would never do anything like that to you, and even most of the time these are going to be givens, okay?
Okay.
So you theoretically could solve it if you had other things, but like I said, if you had to do an intersection where you're intersecting those two lines, that's pretty much math. So not anything that we're going to deal with, okay? So I mean, it's good suggestion, but not quite as simple, okay?
Okay.
Does that make sense now?
Yes.
Because see, here's the thing. You don't really know what this distance is. You know what that distance is horizontally, okay? So to solve that slope distance is a little bit more involved. So it's not, I mean, it's doable. It's not that big of a deal, but we won't deal with it. All right, so to get my EVC elevation, I'm going to take the PVI elevation plus the grade going out. Now, if he had a negative grade, then it would be plus or minus, but it's not going, it's the same positive direction. And again, I'm traveling 175 feet from here, so it's actually 1.75 stations. So we're going to go up, but we're going to go up at a different rate. 1.75 times that slope rate, it's like 2.19 essentially. So let's see what I came up. You guys can verify this. I had 212.19 as my elevation. Anybody concur with that?
Yes.
All right, so EVC now we know is 87.55, and the elevation of that guy is 212. 212.19 essentially. So we now need to calculate R, which is the rate of change of grade for this. So that's defined as grade 2 minus grade 1 divided by L. Grade 2, this is grade 2, so that's 1.25% minus a minus 3 divided by L, and L is expressed in stations, so you just convert that. Basically, you're just dividing it by 100, or you're taking that and just multiply or moving that decimal place over. So when we get this number, we should be getting, looks like, you guys can verify it. It looks like I'm getting a positive 1.2143. Anybody agree with that?
Yeah.
So that's the amount of percent change that's happening along this parabola as you're traveling in distance of stations. Okay. So in other words, that slope is changing as we go across here. So it starts out at 3%, and then at some point it bottoms out to 0, and then it's going to come back and end up at 1.25, and this is telling you the rate that that's happening. So we can now write equation of parabola equation of parabola is y is equal to r over 2. So that's going to be 1.2143 divided by 2 times x squared plus g1x. G1 is -3 plus the elevation of the BVC. So I did this on the board with you the other day. We actually did it for the one that we were laying out. So there's my equation. So who can tell me how we check this to make sure this equation is correct? What do we plug into this equation to verify it? Well, we already know this station right here. So if we plug in 350, actually if we plug in 3.5 for x, what should we get as our answer?
+87 55.
Yeah, we should get, well, we won't get 8755. We'll get the elevation of 8755, right? So what should come out of there is 212.19, okay? Let's try that and verify that and see if that works, okay? Now, if that doesn't work, then we set up something wrong. So I always do that as a check. And don't forget to square that that first x, because that's an easy mistake. So when I plugged 3.5 into this equation and I ran the equation through, I came up with 212.19. Anybody else get that number?
Yeah.
Okay, so that's a check. So we know that our equation's good. Okay, so we know that in order to do this, we would have had to calculate R right, and we plugged everything in. So we know that this is a good equation. Okay, so now the actual problems, what we're dealing with is we're trying to solve where is the low spot. So in other words, I want to know somewhere here is a low spot. Okay, so I want to know where is that thing? Where does it occur? And I want to know what its elevation is, okay? So we're going to use that little equation that I just showed you. To get the location of the low spot in terms of x, we take -g1 divided by r. So we just plug that in. So g1 is a -3. So a negative minus a negative becomes positive, and r was 1.2143. So this will be the amount of distance from the BVC to the low point in terms of stations. So let's see what we come up with. And I get 2.4706 stations. Anybody agree with that?
Yep.
Does that number make sense? In other words, is it possible for that station to be in this vertical curve?
Yes.
And why are you saying yes?
If we go off our distance would be 3.5 stations
Right?
from the start point to the end point.
Yep.
And then that point would be 2.47. So
Yep.
It seems like it's right.
Yeah, it seems like it makes sense, right? So if this number was greater than 3.5, or it was negative, greater than 3.5 would say you're out here, which is impossible. And less than 0 would be over here, which would also be impossible. So this does make sense, right? So we're going to take, and we're going to plug this number into this equation, 2.4706 for x. And that is going to give us what the elevation of the low point is. So let's try that now. You guys verify me, because my calculator is not that swift. So maybe it's just me that's not that swift using it, which is probably the case. Not sure I got a right answer, but I got an answer. So I'm going to put this answer down. I want somebody else to see if they got that number. I might check it again. I don't agree with that now. I'm getting something different. Anybody get a different number?
Yeah.
Okay, let me see what you got. Hold on a minute, Shelley. I'll write mine out there and you see if you agree with me. I knew I calculated something wrong. I just got to get used to this calculator. I got 211,
Oh,
54. Does that make sense?
I got
Yeah,
a different
that's what
number.
I got.
Okay, you got a different number. Anybody agree with me?
I got the same answer.
All right, let's try this one more time. We should all agree, though. I just think it's how we're inputting it. Let's just try that one more time. Sounds like you guys are having as much calculator issues as I do. I think that's going to be right. The other one just sounded a little low, so. I just got the same thing, so I'm going to think. And Jake, you agreed with me, right?
Yeah, I recalculated. I got the same answer.
Okay, I did too. So we're going to go with that number. I'm sure it's correct. All right. So who can tell me now how we would get the station of this thing? So we know the station of the BVC, right? And this distance is with respect to the BVC. So the low point station is going to be equal to BVC station plus X. So in this case, that's going to be 8450 plus 247.06. So notice this is in stations, but I'm converting it to feet. Okay. So you kind of have to know when you're working in feet with these problems and when you want to work with stations. So this gives me a station here of 86 plus 97.06. So there's your station and there's your elevation. So these two things would be critical. Anybody get that station?
Yep.
Okay. Why are those critical points on this highway? What's happening there?
Well, that's where the parabola would level out.
Okay, so what's happening there besides that? I agree with you 100%. What's happening when it rains, Jake?
It's level, so the water stays.
Yeah, so you got water coming down this way on you. You got water coming down this way on you, and guess where it's going to pool? Right there. You guys ever been on a road where there's water pooling on a rainy day because either the catch basin's clogged or it can't take that much water in? Anybody ever seen that happen?
Yeah.
Yeah, absolutely. Well, that water is pooling in the low spot, and it's pooling because either, like I said, you've got a clog and a catch basin, or you don't have that catch basin have enough capacity because it's only designed for a certain type of storm, and if that storm exceeds the amount of water coming into it that it was designed for, it's gonna pool. So it's a dangerous situation, especially on high-speed roads. Okay, get the idea? So when you're driving down roads today or wherever, you hit a dip, look left and right, and you're going to see a catch basin there, or you're going to see a ditch that it's sheeting off into. This is how this is how you calculate this stuff. Okay. Any questions? This kind of did a whole problem because we had to solve BVC station elevation, EVC, R, Y, and in this case, we actually got to do a low point. You can do the high point works the same way. If it's a high point, you still use this equation. It'll just give you the location to the high point, plug that number back into your equation of parabola gives you your elevation, and then you just solve your station. So X is always measured from the BVC to that point out there, okay? And X could never be greater than L, okay? So if this is L, you could never have an X greater than that or less than 0. Any questions? Okay, well, if you guys haven't had a chance to look at chapter 17, I definitely suggest that you do. Otherwise, we're going to go ahead and move on. We're going to look at intersections today. So you guys do have this out there now. Like I said, you have some stuff here we're going to want to take a look at. But I do have some sheets out there. I have the some typical section stuff, and there's the lecture notes right there. We're going to take a look at this Tylersville Road intersection because they're really busy. But we're going to lay one out, which is kind of neat to see how this is done. It's really no different, but when you have two intersecting kind of things going on, then we got to look at that. So let's jump into these. And if you guys have any questions while we're going through this, please stop me, and we'll take a look at it. Okay, so we're going to look at some concepts of intersections, looking at reading plans. Now, the big thing I'm going to present today are what are called typical sections, because these things are happening left or right of what's going on in your profile. So when I introduced those last Thursday, what did we use our typical section for last week? What was that? What information were we getting from the typical section?
That was the top of the curb.
Right. We were getting the top of curb information, and we needed that so we could do our cut and fills, right?
Oh, yes.
And what was the typical section tied to, Jake?
The stations.
Well, station of what?
The horizontal distance.
It was tied to the station of the center line, okay?
Oh, yeah.
Yeah, so you're getting your initial grade information from the center line, and then you're working left or right from that, okay? So just keep that in mind, because depending on what station you're at, that typical section is going to float up or down to match where the center line elevation is, okay? And in our case, we found there was a relationship between the center line and the back of curb. It was what, 0.2, wasn't it? I think.
Yes.
0.2 feet. So that was the same throughout the whole process. But if we have other things going on left or right, like ditch sections and those kind of things, that can change a little bit too. So we'll look at those, and we're just going to talk about intersection layout, which is what we're going to do. All right. So, you know, when you're doing any kind of layout, we've talked about this a million times, you're going to do line grade. In this case, we're going to look at cross section as well. So we did a little bit last week. We're going to use a little bit more this week. Line just refers to horizontal location. Northing and easting, station offset, X and Y, whichever format you're working in. So that comes from the plan view. And we're going to take a look at a plan view of that Tylersville Road section today again, looking at the intersection on that. Now remember, highways, they typically work in what's called plan and profile. So it isn't just one sheet. So that makes it a little bit more involved, although it's nice because you can see both at the same time. So again, there's your typical thing, plan view. We've looked at this before. Grade, of course, is your vertical plane. That's established by your profile. So that's where your major grade information comes from, and it's given to you in station and elevation, and you also have a slope and or a grade. So this is a very simple roadway profile where stations are at the bottom. You know, you've got the graph over here. This is elevations. In this case, my blue line is representing a proposed and the green is representing existing. Notice right here, this is a vertical curve, okay? So we've got a parabola starting at that little blue dot and it runs to that blue dot. And that little pinpoint symbol right there is showing you, actually, in this case, this is a low spot. So that's a low spot right there. So it actually calculated that for you. And that's what you see on a set of plans. So the cross section is given by a vertical plane as well, but it's primarily station, and it's actually not station because you're typically at a unique station, but you're looking at offset left or right from whatever station you are, and then the elevation and or slope and grade. So these guys can be really involved, as we'll see. So we use that term typical section primarily. On highways, you're going to have multiple typical sections, not just one. So this is a really simple typical section. This is the kind of typical section. This is the Hamilton County typical section that they use for subdivision. Okay, so it's really pretty straightforward. You have a relationship. This is your curb datum, so it's showing you how far above that. There's your on that side over there. That's showing you your elevation of your profile, and this is showing you that the curb is above that a little bit. So there's information about that. We have a slope right here, a slope right here, and then these are your ties into your existing ground. So this guy is doing a whole lot of work right here, and it's all just linked to the center line. All right, so let's talk about intersections a little bit. You guys all drive through them all the time, okay? It's just generally an area where you have two or more roadways join or cross. Okay, now they might cross each other, which means they're maybe not at grade intersections, or they're crossing directly at grade, so there's a difference. Also, this includes the roadway and the roadside facilities and any traffic movement within and out of that. So 3 general types of roadway crossings are encountered, what we call at-grade intersections, and that's what we're going to be looking at. At grade, that means the 2 or more streets that intersect, they are touching at the same grade, okay? So if you're at grade-separated intersection, then you have ramps that come in and off of. So an interstate entrance and exit ramp would be an example of that. You have 2 intersecting roads, but one is above or below the main highway. So you have a ramp up and down to that. Those get really, really involved, and we're of course not going to be dealing with that. And then you have interchange ramps, you know, big ones like cloverleafs and those kind of things. So those are all very, very involved. We're just going to be looking at this very simplistic at-grade intersection. But when I say it's simplistic, they're not so easy to design sometimes because you have to make sure everything's tied together. You also have to have certain grade minimums and, you know, typical sections and all of that. So actually, a grade separated type of intersection is a little bit easier because all you're dealing with is the ramp in and out. So from a design standpoint, from a layout standpoint and a building standpoint, these guys are going to be more involved. So this is easier to build. So here's some terminology associated with these. I'm sure you guys have probably might be aware of this, but basically, we typically have 2 streets intersect. One's usually a major and one's a minor. Now, that's usually defined, what we call a major and a minor. That's defined by what kind of traffic is being handled. So you notice we've got 4 lanes of traffic here and only 2 here. So that makes a difference. You have pavement edges on both of these. Now, they could be curbed or non-curbed, or one could be curbed and one could be just edge. So it's different. And then you have usually a radius that connects these guys. That's called a corner radius. And, you know, that's going to vary. Minimum would probably be about 25 feet to get a normal vehicle around it. But if you're dealing with truck traffic, that's probably going to be a bigger type of radius to be able to handle that truck. Sometimes I'll use channelization. So this is an example of channelization. So this gets more involved because this is actually starting to thread out or open up, and then we've got lanes that separate out here. We have a channelizing type of island, which may be either with like a concrete barrier, you guys have all seen that, or it might just be with paint. So it just depends. So this is your actually turning roadway area here, and then this would be a radius that would be needed again for whatever kind of traffic you're designing it for. And notice this stippling, this cross-hatching is indicating the limits of the actual intersection. So this actually goes a little bit beyond what you might consider a normal. A lot of people might just call this the intersection here, but really from a design standpoint, you're designing it back a little bit further in both directions. Also, there's a typical or some kind of angle of intersection that's occurring. Now, a lot of times we like to keep that 90 degrees because that gives you the best sight distance, but you know, any intersection you guys are aware of, they come in at all different angles. And if they're at if they're at some weird angle, I mean, obviously they're going to be signalized somehow, or they're going to have stop signs or some kind of thing like that going on. So we'll also see that too. But signalization is a whole nother issue, and we're not even going to worry about that. So essentially what we're going to be doing is taking and laying out this kind of thing on our intersection. Now we're not going to have a four-way. We're just going to have a three-way. So we're going to have one road going this way, but we're going to be laying out the pavement details on it. But we're going to have to look at a profile on this road and a profile on that road, and then typical sections. So we'll see how that all works. Okay, so the major street, that's the one that has the greater volume, as I already said. The minor is the lesser volume. Intersection limits, that usually is talking about, again, highway engineers are going to talk about all the things that are affected by that roadway intersection design, the striping and, you know, signalization, everything that goes into it. That angle of intersection, that's formed by the geometry of intersecting street center lines, and sometimes they're not lines. Sometimes they're curves. You could have two curves that intersect, so you really don't have a true angle at that point. It's a little bit more involved. As we'll see, I think that Tylersville intersection has two curves that it's dealing with. So intersecting legs, these are the segments that connect to the intersection. And this is used by the approaching and departing stuff. So if we look back at this guy, these are your legs right here. This is your ending leg and beginning leg kind of thing. Okay, auxiliary lanes, these would be added if you want to accommodate turning vehicles. That's not always going to happen. So if you think about the typical street where you're coming off of on an intersection, and you're like, say, coming into a simple subdivision, you're not going to have auxiliary lanes. Okay, channelization, again, that's a more involved thing. That's going to help delineate areas and then keep your movements less conflicting. So the idea is you want that flow in there and out of that as well as possible. Okay, turning roadways. So a lot of this stuff we're not going to deal with, but these are just some things that you see in there, okay? So your intersecting roadway configuration, the geometry, and what we're talking about geometry there would be the horizontal geometry. It's going to be usually composed of several different approaches. If you have three approaches or three legs, it might be called a T, a skewed T, or a Y. So a T type would be a 90-degree primarily intersection. A skewed T would be the angle would be greater than 90 on one side and less than 90 on the other. And a Y, of course, coming in just like a Y. Then you have the four approaches or four legs, right angles or offsets or oblique. So we got some pictures here that are kind of showing you. So here's your classic T on a 3 approach. Here's kind of your skewed T, and here's your Y. And again, the cross-hatching is showing you what's considered the actual intersection in this. So if you're doing layout of just the intersection or you're doing the design, that's what you're designing right there, okay? So here's the 4 approaches. I guess you guys have all seen these, I'm sure. This is pretty classic. These are also the kind, we see a lot of these around here. And then these oblique ones. We are actually around here have 5-way intersections. Anybody's ever seen a 5-way intersection? We have 5 approaches. Anybody?
Yeah, sometimes like in like a rural downtown area where there's a lot of hills.
Well, there's some around here. They're just not as common. But yeah, it's not necessarily rural. You could have it in other areas too. Sometimes our urban areas will have those. So they're not uncommon, but the 3 approaches and the 4 approaches is probably the most common. Okay. Now we're going to be doing this classic T 3 approaches is what we're going to be looking at. Okay. Simplest kind of case, but really what you see in one kind of applies to all of them. Also, by the way, these again, I'm showing these as tangent lines. But as we're going to see, that's not always true. Okay, they can be curves, and that gets a little bit more involved, even of course. So the pavement corner radius is a little curve that connects from pavement of one street to the pavement of the other. So that can vary based on how they design it. The simplest type is to just put a little curb fillet radius in there. So that would be like using the fillet command in AutoCAD, where you just give it a radius and you just fillet the two pavement lines together. That's a preferred design. It's easiest to lay out. It's the easiest to grade. That's what we're going to be working with. But they also have more involved ones, like you have tapered ones. So that approximates what's called a compound curve. And a compound curve is two curves put together or three curves put together. And compound curve turning radiuses are also used. And I've laid out this type, the simple curve. I think I've probably laid out all of these in the real world. So I've done compound and simple, tapered as well. These compounds are a lot more involved. We'll take a look at that set of plans and see what we've got going on. By the way, these connecting corners are sometimes referred to as curb return. So you hear a lot of people use that term, the curb return. So what they're talking about, this is this kind of thing. So this is an example of the three types right here. Here we see the simple radius. So here you have your pavement line of the one approach, the pavement of the other approach, and you're just placing this curve in here with that radius value. So notice it says R1. That means it just has one radius associated with it. So here's the tapered kind of concept. So you notice that we're coming in, this line is parallel to the center line, but the taper starts to deviate from that. And what it's doing is it's getting wider. So you notice it's at the fixed value here, it gets wider here. Same thing happening here. And then we fill at the tapers. So you've got 1, 2, 3, 4 more geometry points in here than this. Just the two here, basically PCPT. Here you have a taper point, another taper point. So these get more involved. And then here's an example of the compound curve, and this is what they call a three-centered compound. So notice you have your parallel line here and parallel line here to the center line, and then you put a small curve in here, but it has a large radius. Then you have a smaller curve that goes from here to here, and then that same curve radius coming in here. So notice you've got R1 and then R2. So these curves, by the way, they're all tangent to each other. So these are all tangent curves. I've laid this type of curve. I've laid this out for sure, and I've laid this. I've probably done tapered too. I just can't remember doing it. So the typical section is what we're going to encounter here, but I want to switch over real quick. I want to look at that Tylersville set of plans with you real quick. So let me escape out of here. You guys should be able to pull this up on yours. I'm looking at this thing called the Tylersville Road Intersections PDF. And this, let me see if I can zoom this up. This is an intersection detail, and you can see it's quite involved. Now, as we look at this, there is a center line right here, if everybody can see that, and a center line right here, and these are actually two curves. So we have a curve coming in here, and we have another curve. So this is a four-way approach, but it's not on tangents, it's on curves, which makes it a lot more involved. Now, if we look at the curb radiuses here, we can see the things we were just talking about. Does everybody see there's a radius over here, and it says it's 50 feet right here? Does everybody see what I'm talking about?
Yep.
And it's got, if you notice, all right, I want you to notice something here. This is kind of important to understand too. Notice it has a station there. 409 plus 30, 51. That is the station of, let's see, this is 747. So that's the station for where this curve PC is, if you will. And this 299, 6692 station is referenced to Tylersville. So these stations are actually referenced to two different center lines. Notice they also have two different offsets. You have a 42-foot offset here and an 18-foot offset to that, but the radius itself is 50. So that's just a simple curve. But however, this is anything but simple, because this pavement right here, it looks like it might be tapered. It's hard to tell here. So this could be a taper coming into that arc, and then it's going back into here. And this doesn't look tapered, but it is on an arc. So you have an arc attaching to an arc, potentially attaching to a taper. And there's one over here that's definitely tapered. I think you can see this one might be on a taper also. It may not be. It's kind of hard to see. There's a lot of stuff going on here, but I do notice that it says 30 feet right here. Let's see if there's a taper down the road here. Let's see. There's 30. Yeah, there's. Okay, so it's not tapered. So this is parallel. So this line is a parallel line, but notice there was a taper that came out here. So this thing is very, very complex. And then down below, what we're looking at is we're looking at the profile, but this happens to be the profile of Tylersville Road, not of this. So to get the grade information coming into it from 747, you'd have to go to another sheet that would have the profile for 747. So again, this profile down here is just for the profile sitting here. And if we look at this, this is a pretty complex profile as well, because there is a vertical curve right here coming in. So this thing is happening in a vertical curve. So not only do you have horizontal curves going on this, but you also have vertical curves going on this. So it's pretty involved set of plans. Now, somewhere down the road here, let's see. Well, these are a typical section. We'll come back to this. Here's an intersection detail that is showing you how to lay the grades out. So what this is showing, this is a really well done set of plans, because what you're noticing is it's giving you center line information. Okay, there's your stations and grades, and then it's giving you grade information along this actually doesn't have curb on it. So this would be the edge of pavement grades. So they've worked all of this information out for you. So whoever was doing this layout, it would be pretty easy to lay this out. Okay, but this is an intersection detail, more or less, and we're going to be working off something like this as we do ours. But remember, ours is going to be a lot simpler, because the line coming through here is going to be a straight tangent line, and the other line is going to be 90 degrees. Everybody get the idea here, though? This is a real, like I said, real intersection. And if anybody knows where 747 and Tylersville intersect, this is what it's based on right here. There's another sheet. This is showing us some other details associated with this, but primarily this is dealing with drainage. Okay, so this is a typical section, and these are very complex. We're going to look at these, but these are just a few of the typical sections that are governing what's happening out there. So what it's showing us here is what's going on left and right of the center line. So from the center line, this is your center line of what's going over left. There actually is a curb over here. Over to the right, there isn't a curb, but there's a shoulder, then there's a ditch, and then it goes back up. Again, this is a different typical section for different stations. So again, there's curb on the left side, not on the right side. And you notice then when we get to this is called a normal section. And you got pavement on the left side, shoulder, ditch, and then you got pavement on the right side, shoulder, ditch. You can see how these get real involved. And if you notice down below, it's kind of hard to read. But if you notice down here, what this is saying is that this typical section is going to be applied from that station to that station. When you get down to this typical section, then you're going from that station to that station. So, I mean, these are really involved, okay? And again, ours is going to be pretty simple. Any questions before we pop back? All right, so let's come back here. All right, so we're going to take a look at typical sections. Just want to make sure I didn't cover. Okay, typical section. So these guys are cross-sectional views of your roadway corridor, and so there's going to be two kind of types that you see on highways and any kind of roadway. You either have what's called a structural typical section or geometric. Now, sometimes you have both incorporated in it, but primarily a structural defines the type and amount of material that's used for construction purposes. So you'll see like how much pavements, if you're doing like pavement, you're going to have like some rock and then another layer of rock, which is like crushed gravel. And then you maybe have a lift of asphalt, and then maybe you have 3 lifts of asphalt, and then what's called a wearing course or a final course. So this information is your structural information. If it's poured concrete, you'll probably have like some rock, and then you'll have your poured concrete, and that's going to be it. So it just depends. The geometric is the more important of the two for layout purposes, because it's going to define both the vertical and the horizontal location for critical points within that design corridor, left and right of your center line. And that's what we're going to take a look at, is the geometric typical section. So let's take a look at some typical section terminology. You have what's called a traveled way, which is basically the portion of the roadway that actually provides for the movement of vehicles. So that's essentially your pavement. The roadway itself is the portion of the roadway provided for vehicle use, but the traveled way might include shoulders, those kind of things. And then you have the shoulder, that's the piece left and right. Not all roads are going to have shoulders. That's just again, depends on the size of the road and the type of vehicles it's going to handle. We have a median, that's your physical or painted separation. You really don't have a true median and just the two lanes where you just have a stripe, but basically your stripe is it. But if you have a true divided highway, then it's usually that strip of grass between, and a lot of times they're using that for drainage purposes. Then you have drainage channels, and those can occur left or right of your pavement, or they can occur in the middle, in the median, and they can occur both places. And then you have what's called a clear zone, the distance from your edge of traveled way to either a fixed obstacle or a non-traversable slope, which means you can't drive on it. That's too steep. So this is kind of showing you those generalized terms. So notice we have the pavement center line, which most everything is given off of. So here's our traveled way. Essentially, that's your area where your vehicle's traveling on. Your shoulder is outside of that. You have horizontal and vertical slopes. These are variable values. This thing's called a hinge point. So that allows this thing to travel up or down at different slope rates to hit the existing ground. So this guy's indicating kind of your existing ground that you're tying into, and that's existing ground on that side. This is showing you kind of things like, how much topsoil and seeding is going on, and this is where they're actually doing the cuts. Most of the cuts and fills are happening in here, but you could have some cut and fill going on out here, certainly, because this is showing you a fill slope, and this is showing what's called a cut slope. So let's look at slopes. So slopes, you're going to see associated with typical sections. They come in different types of displays. And in fact, on any typical section, you're liable to see all three of these. So a lot of times things are going to be expressed in percent grade. So we already know what that is. That's your change in elevation divided by your change in horizontal distance multiplied by 100. So if you say 6%, you're saying it's 6 units of rise or fall and 100 feet of run. I should say units, because this could be inch per inch or feet per foot or meter per meter. So the other way we express things is what we call a horizontal ratio, or a ratio of horizontal to vertical ratio. Again, it's basically a vertical divided by a horizontal distance kind of concept, but it's not expressed as rise over run. We would see this written like this. So if we see this is, you would state this as a 3-to-1 slope, but the 3 is the horizontal distance and the 1 is the vertical. So 3-to-1 slope is actually 1/3. And if you would take 1 divided by 3, you get 0.33333. You multiply that by 100 and it tells you you've got a 33.33% grade. So this is a steep slope, and that's pretty maximum around here. You wouldn't see anything any steeper than this, 3-to-1. As this number, by the way, gets smaller, your slope gets steeper. So a 2-to-1 slope is going to be steeper than a 3-to-1, but a 4-to-1 will be flatter. We'll take a look at this. The last kind of thing you're going to see on a typical section is this thing called an equivalence. So that's usually expressed in inch per foot. So in other words, these guys right here are unitless. Percent grades and horizontal to vertical ratios are unitless, but equivalences actually have units associated with them. So a 1/4 inch per foot, if you're doing that in terms of a fraction, you want to make sure you convert things right. So in other words, I would have a 1/4 inch per 12 inches. That would be my slope rate if I wanted to convert it this way. So you have to be careful when you use this kind, because it works. It's kind of easy to make a mistake. let's see if we can, I want to see if we can look at some of those typical sections real quick we were just looking at and show you what I'm talking about here. Let's go to the, let's see, pull this up. Oh, okay, here we go. All right, so if you notice, yeah, you can see pretty much everything I was just talking about right here. So notice you see this, that's 0.04, that's 0.08. Does anybody know what that's saying?
Slope grade?
Yes, what's it rated in? Is that a percent or is that feet per foot?
Looks like a percent.
It is a, no, it's not a percent.
Oh.
It doesn't tell you, but it would have percent after it, okay? So that's actually 0.04 feet per foot. So in terms of percent, what would that slope be? Well, if you multiplied it by 100, what would you get?
That'd be 4%.
That would be 4%. So technically, that's saying 4% grade, 8% grade, but now we get here and you notice it's no longer in percentage, it's into a horizontal to vertical ratio. So this is saying it's a 3-to-1. So it's actually changing into a 33.3% grade. Okay, so notice we've got, so this is actually isn't even in percent. So a lot of them do it all different. Let me see if I can find some equivalences on here. I don't know if we have that. It looks like, yeah, notice there's a 12-to-1 slope, but that's really flat. 4% grade, 3-to-1. I don't see any equivalences, but they are using different values, and that's the thing you got to watch with these guys. These typical sections can be pretty rough until you get used to them. Okay, everybody get the idea? So let's flip back over here. All right, so we saw percent grade on that, except it was expressed in feet per foot. We saw the ratio, but we didn't see an equivalence on that. Okay, so here's an example of a typical section that I'm showing you all of those things on it, built into it. So notice as we look at this, my roadway is in format of percent grade. Everybody see that? Right? The roadway's in terms of percent grade, 2%.
Yep.
And then this is expressed as a 4-to-1 ratio. And then this is equivalency of 4 inches equal to 1 foot. And this is also an equivalency of a 1/4 inch per foot. So this is an example. This is actually the Hamilton County typical section that they use. And notice this is called a half section. What does that mean if it says a half section? Anybody tell me?
It's just showing one side of the road.
Right, so what this is essentially saying is this is symmetric, okay? So this would flip over on the other side. Now, if you think about those typical sections we just looked at the highway, they were not symmetric. So they were showing you different distances on the left and on the right, okay? So that's important to understand as well as we look at this. So this is allowing me to apply this guy at any station I want to. So I can come to 800. I know what 800 elevation is there. I can tell you what the edge of pavement's going to be. I can tell you what this ditch elevation is going to be. I can tell you what this break point is, because this might be where we have pavement, or this might be our sidewalk. And I can even tell you what the base of this utility pole should be based on what this typical section is doing. So we're going to walk through this, and I'm going to show you how to do this little process, because this is a great little tool. So what we want to do is determine these critical points, okay? So we're going to assume that this point 1 is the location of the actual center line of the road. So we want to know what the drop is from here to here at 2%. And then we're going to want to know what the drop is from here to here, because if I know this elevation, I can tell you what that ditch is really easily, okay? Then I want to know what the drop or the rise is from here to the center line, because again, if this is 800 and I know I just come up or down based on that number there, same thing here. So this is how we're going to use that typical section. We're going to figure out what I call kind of a template numbers that I'm going to use to determine this. So we're going to have a 2% grade down. What's the distance that the 2% is running at? That's 10 feet, right? 10 feet from the center over to the edge of pavement, correct?
Yes.
How far is that 4-to-1 slope traveling?
5 feet from the slope distance.
And you're getting 5 feet from where? Because it says it's what? 15 minus the 10, right? Does everybody agree with that?
Yeah.
Okay, so that's important too. And also notice, in this case, my typical section isn't necessarily drawn to scale. And that's also true. So don't let that influence you when you calculate these things. Okay, so we then have what is it, 4 inches per 1 foot? Is that right? Over a distance of, what was that, 5 feet, right? And then we have another 5-foot distance with a slope of 1/4 inch per foot. So what we're going to do is come up with cuts or fills for that 1, 2, 3, 4, and 5 position. So what we're going to do is we're going to assume that 0.1 is equal to 0. And the reason we're going to do that is we're going to then reference everything back to that. So that's going to be our reference. So I'm going to kick this over to the white screen here, and we're going to work this thing out and show you how convenient this is if you do it this way. And give me a sec here. I'm going to work this over to my screen here real quick. Come back to this guy here. All right, so let's clean this mess up. I'm going to simply draw that typical section real quick, and then we'll work these numbers out. And you'll see that this is a really, really good thing to do. In fact, when we would, out in the field, I used to do this all the time. First thing I'd do is sit down and take and construct my typical sections. So what I know is that my pavement is sloping. Oops, again, why is that not doing that? All right, so hold on a minute. Something's wrong here. I got something turned off. Yeah. It's so easy to get this thing worked out. Huh. All right. Give me a sec. There we go. All right. Okay, good. All right, so let me draw. So we've got our pavement coming down at a 2%. Then we got that ditch section going down. Then it comes back up. Then it slopes again like that. So I think those are the different slope rates. So I'm going to write the information down on there. So this is at 2%. Okay, this is at 2%. And this is we're gonna call this 0.2. This is, what do we say? That's a 4-to-1 slope. Is that right? 4-to-1. So
Yeah.
that's the 3. This is 0.4, and this is 4 inches per foot, I think, right? And then this was a 1/4 inch per foot. So we want to know, we're going to call this 0, okay? And so if we're below 0, then we're going to call it negative. If we're above 0, then we're going to call it positive. Everybody get the idea? And I think these are all 5-foot distances. So the first thing I'm going to solve is the distance at 2%. So we know that we have 2%, which would be 2% divided by 100 times, that was 10 feet, wasn't it? Wasn't this pavement 10 feet? All right, so what's the drop there? So we have 2 divided by 100 times 10. So how much is it dropping from the center line to the edge of pavement in 10 feet?
0.2 feet.
Yeah, so this is 0.2 feet. So what we would do is we would say that this right here, as related to the center line, would be negative 0.2 feet. Now, here's why I'm doing this. If I know that I'm at station, let's say 700, and it's 800 feet, all I have to do is take 800 and add to it this negative 0.2, and it tells me that that pavement is at 799.8, right? Everybody see what I'm doing? if I go to the next station and it tells me that I'm at its elevation 850, then I can just, all I have to do is subtract 2/10 and I got the elevation, the edge of pavement. So I can do this wherever I need to. Does everybody see the idea? Everybody get the idea? Anybody not
Yeah,
understand what I'm saying? No questions? Anybody there?
Yeah, I'm good.
Okay, all right. So now we want to know what the drop is from point 3 to the center line. But first we have to determine what this is, right? So 4-to-1 says that you have 1 unit of rise in 4 units of run. Does everybody agree with that? That's what that's saying. 1 unit of rise, 4 units of run. And that's going to be equal to X amount of drop or rise in 5 units, 5 feet. So if we solve for X in this proportion, what is that telling us? What do we get? Basically what, just 5 feet divided by 4? Does everybody agree with that?
1.25.
And what's the unit on it?
That'd be feet.
Okay, so now, what is the drop from here to here? Well, this drop is from what? From here to here, right?
Yes.
So we're already what? 2/10 below, correct? So we're going to add to this 0.2, which will give us a negative 1.45 feet. So what this tells me is that this point is 1.45 feet below the center line. Does everybody see what I'm doing? So I can now write this up here, 1.45. So this drop is reference to the center line because remember, my center line, this is where I'm getting my elevation. And you got to understand this too. We're not looking at a profile here, guys. The profile is coming at you, okay? The profile is coming at you. You're not looking at the profile. Is everybody seeing what I'm saying here?
Yes.
I'm not getting much. All right, well, I'm gonna move
I guess
on.
the
Go ahead.
reason why we're not just doing it manually, like calculating every foot, is because if we were to deal with larger distances than what we're dealing with now, it would be a lot harder to do that.
What do you mean every foot? Let me qualify that for you. I want to see what you're saying exactly.
So if we started at that point that's negative 1.45 below, if we were just to calculate the number 4 point, we could just go off of how it would raise 4 inches per every foot.
Are you talking about this number here?
Yes.
Okay, so you're saying, why don't I use that number here?
Oh no. If if we're on our point negative 1.45, and then we wanted to find 0.4.
Oh, okay, I haven't done that yet.
We could just, if that distance is just 5 feet, then we would say that it would rise 4 inches per every foot. So we can just multiply 4 inches by 5 and then put that in decimal and then add it to 1.45.
And that's exactly what we're going to do. And what that's going to do for us, though, is give us reference back to here. See, the whole idea is you want to make this simple. This is the number you're going to know right here. See, the profile. So this says, okay, if I want to put the ditch in, all I need to do is take the profile centerline elevation and subtract 145. If I want to do the face of the sidewalk, I just take that elevation and add or subtract whatever that number is. Do you see what I'm getting at here?
Yep.
That's going to make it really simple for me, because if I have to do this every 25 feet, I don't want to go back through and calculate all this stuff. All I need to know is what is the drop from here to here, or what is the drop from here to the center line, here to the center line, here to the center line. Because I can look on the profile and get this number real quickly. Is that making sense now?
Yeah.
So we're going to calculate that number 4. So what we did here, this was for 3 right here. This was for 2. We're going to do it for 4 now. So Jake, you just told me it's what, 4 inches of rise per feet. I'm going to put this in feet per foot, okay, to keep that unit square, right?
Yeah.
So what I want to know then is what is the rise in feet over a distance of 5 feet? So that gives me an X value of what? We've got,
And you can convert that 5 feet to inches too.
well, you can, but I want to be in feet actually, see? So since this is unitless here, when I just bring in X will be in feet too. See that?
Okay.
Okay, so you just got to make it, just make sure you're in the common unit. So I'm going to take, in this case, I'm going to take 5 times 4, divide it by 12. That gives me basically a positive 1.67. Now this is a positive because I'm going uphill. See, this was technically a negative, right? Going downhill. And I added to this really, I guess I could change that because that's a negative actually. You see what I'm saying?
Yep.
Okay, so we're going to take this 1.67 positive, and we're going to add to it a negative 1.45 because we know we're already down that amount, right? So this gives me a rise of 0.217 feet. Anybody get that number?
Yep.
Okay, so since only one person is doing this, I'm going to assume we're all good. But we'll see how good you guys are on a quiz. All right, so this is going to be, you got to help, you got to input a little bit on this, guys, if you want to get anything out of this. So what this is telling me is that this point is 2.17 feet above the center line. So if you, again, you know what this elevation is here, and you need to stake out the face of the sidewalk, and I need to know what its elevation is. You just come find that elevation on the profile, and you just add that to it, and it works every time. I don't have to recalculate that every time. So we have one more to do here. We're going to do it for 0.5. We're going to reference that. So we know that we have a 1/4 inch per foot, which is the same thing as a 1/4 inch per 12. Agreed?
And then you
We
can
wanna
make that
know-
a decimal.
Well, we could, but I'm just doing it this way for now.
Okay.
So, and I know that my rise over my run has to be equal to my rise. I don't know, but my run, we also know is 5 feet, right? Because all of that was also a 5 foot distance. So when we solve that proportion, let's see what we get. 0.25 times 5 divided by 12. I get X being a plus because it's going uphill 104 feet. And so my actual answer is going to be 0.104 feet positive plus the 0.217. And we get a total number here of plus 0.32. Essentially, that's it. So this number here then, so this would be the right-of-way point. So if you need to stake the right-of-way stake out, and then you need to grade it, you know that it's going to be plus 0.32 feet. So this one's critical, that one's a good number, that's a good number, and that's a good number. I never even really need to look at those anymore. Okay, does everybody see what I've done there to make it simple?
Yeah.
Okay, so if we go back to the PowerPoint, you'll see I think I've got that worked out for us. There's your numbers right there. You see those are, so that's what we started with. That's what we ended up with, and that's exactly what we just said. And sometimes I'll carry those out a little bit further if you want to do that. So you could use this to calculate these prominent points really easily. And those are the kind of the things that, you know, you're going to have to stake your ditch out. You're going to have to stake your sidewalk out. You can do this. And this typical section will work every place it's supposed to. And like I said, this thing could work for miles, and then it may only work for a couple of 100 feet. It just depends on what you're dealing with. Okay, everybody okay with that?
On plans,
Yeah.
if we were to look at this and
Yeah.
calculate this,
Yeah.
would they like label this 1/2 section as like the number 1/2 section?
Well,
And
they
then if
do-
they had a different one for that side, it would be like a number 2 half section.
Yeah, but they don't do it by that. Let me show you about something real quick. I kind of showed you that, but you probably didn't see what I was talking about there. So now that you got that question, you'll see exactly what I'm talking about. Give me a sec here. Let's see. All right. So they do it by station, Jake. So look, see how that says limiting stations? And this typical section is valid from station 302 to station 307. You see that?
Okay.
So that's basically saying you're using this typical section for those stations only. So then coming into that station, you got this typical section from station 299 plus 9220 to station 302 plus 00. So this typical section is different. And notice, by the way, these guys right here, this 9, 6, 3, 4, this is your structural information. And this up here is this is your geometric information. So these typical sections that actually have both. Also notice these are not symmetric. So that's why they're not showing you half sections here, because what's happening on the right of the road is different than what's happening on the left. Okay, did that answer your question, by the way?
Yes.
Okay, so yeah, they do on a highway. They do this by they do that by station. You can see this is really involved. You better be aware what typical section they're using for what station. Otherwise, you're going to lay it out wrong. Okay, so you got to really watch that.
So for these kinds of roads, they would usually do it in full sections, not half sections.
Yeah. So these are full sections, correct? But
Okay.
if it's a simple subdivision street, you might get a half section because it's just a mirror image to cross it. It's pretty straightforward. Okay, does that make sense?
If there was like an exit in between that first normal section and the second normal section, would that
Yep.
be a half section that they would show
Well,
in between those?
You may actually have a whole section. Are you like talking about a ramp kind of thing?
Yeah, like an exit ramp.
Yeah, well, what happens? Do you notice how it says this lane varies right here?
Oh, yeah.
You see how it's going from a 0 to a 12 feet? So what that means is that this is widening from 93.75 to 97.76. It's widening from 0 to 12 feet. You see that?
Yeah.
So there's a widening. These things are so complex because what's happening, that's your taper going on right there. It's widening. It's changing everything. So this thing, it shows you a lot of information, but it really, really varies. So it's pretty involved. It's real involved, actually. Okay. But yeah, that's a great question. Now, I want you to point out something too on this. There were 2 roads on this, right? These typical sections are only for Tylersville. Do you notice that? So there's a whole, and by the way, this is only sheet 1 of sections. There's probably about 5 sheets of sections. So you're going to have maybe 3 sheets of sections for Tylersville and maybe another 3 sheets or more for 747. So when you do highway work, you really got to know what you're doing. Otherwise, you can really, really get in trouble real quick if you don't know how to read typical sections. Okay. But we're going to keep it really simple, okay? But just like anything else you do, if you do it enough, it's not that big of a deal. Okay, any questions then? That was a great question. And that actually kind of just tied right into that. Okay. All right, so if there's no questions, I think that was all I was going to present today. Now, I want to look at what I want to look at with you real quick before we get done here. If you guys have a chance, you should open up this lab here. Let's go ahead and this is what we're going to do on Thursday. So we're going to lay out an intersection out in the front. And I have 3 intersections that are out there. I think we're just going to probably do 2 of them. But let me see the original picture. Okay, so here's the picture. Actually, I just have 2, it looks like. So let's see. So we have, this is the front of the school up here. There's our control point 100. So we're going to do a major, we got a major road coming this way to a minor road. And then we only usually have, we may just do 1 intersection. If we have enough groups, I'll do another intersection right here. So what we're going to do is lay that, we're going to lay the roadway out from this point to this point and this point out. And I'm going to give you guys radial stakeout. So this would be the one. So what we're going to do is get radial stakeout information. So you notice there's 104. So we'll get radial stakeout information for the center line point here, the intersection point, and the other center line, and then we'll get another intersection here, or a stake. So we actually have 1, 2, 3, 4 stakes. One group is going to lay out the center line, but we're actually going to do the edge of pavement. So they would occupy this point, backside the other point, turn a 90, set your offset, turn another 90 and set your offset. They would then come down here, turn a 90, go offset and offset. What would be our offsets on these roads? What's a typical offset for curb?
12 feet?
3 feet. The
Oh,
offset.
3 for the curb.
Yeah, for the curb. Yeah, I'm not talking about the curb itself. This picture, notice, doesn't have the curb information. It doesn't have the distance on it yet, okay? So
Okay.
it does have stations, but we'll get to there in a minute. So the other group then will set up here. I've had another group set up here, backside the intersection point. They'll do the offsets here for this road. And then we have to establish this curve. Anybody know how we might establish that curve? The curb, I guess I should say, not curb. The curve. We've got 2 curves to do there.
It shows the stations for the beginning point
It does.
along one road.
Yeah,
and then
and
the
it's also
station for the other.
it doesn't show the radius, but that radius is going to be really small. So we're not going to deflect around this thing. We're going to set the radius point, and we can do that really easily because we've got the geometry that we'll be able to figure this out. So we'll be able to sit here, backside here, turn an angle and go a distance to set that point, turn an angle and go a distance to set that point, and then we can just occupy that point, backside that one, and just pop in a stake and turn delta over 4, okay, and then we'll just do it that way. So these are going to be real nice layouts. So we're going to lay out the curve. We're going to lay out the 25-foot stations along both. So when we get done, this is essentially what we're going to, this is actually my profile essentially. So it's showing me that we've got an 8% grade going up this way and a 4% grade going this way. We're going to have typical sections that we're going to use for these roads. There's your intersection curb return geometry. So here's your curb back curb information. This street right here is a 37-foot width total. Okay, so we're going to come over that distance, half of 37 plus 3, half of 37 plus 3 this way. This one will be half of 28 plus 3. So we'll work all of that out. But when we get done, we're going to have grade stakes along here, grade stakes along this side, grade stakes along this side. And then we're going to use the typical section to figure out the cuts and fills on this stuff. So this is what we're going to be laying out. And that's the other intersection. I don't know if we'll do both, but so here's the typical sections. We're going to have 2 typical sections we're working with. We're going to use one typical section for the one road and one for another because they're different ones. And this is we're going to be working with this information. So I would suggest, if you could, print this out and read through this before you come on Thursday, because that's going to be real important to the whole process. And then there are some problems in this lab to do, which you could actually kind of start on if you're interested. At the back here, there are questions that you're going to use as typical sections to calculate elevations along selected points here, okay? So that's what we're going to be doing on Thursday. Now, we won't get everything done, but we will get the layout, and we will be able to get, we should easily get this laid out. Well, I shouldn't say easily. It'll take probably 3 hours. But we'll get this thing laid out and we will get it graded. We won't have all the cuts and fills figured out. We'll have to, you guys will have to do that later. And I'm sure that you'll have questions for me. So that'll be very important, okay? So that's what we're doing. And I also have some supplemental information out there for you. Let me go back to that. Let me go back here. So there's all this information. These are all stuff that we just looked at today. There's some supplemental information here about calculating different things. So you might want to look at this because this shows you how to do things about layout. I've got things in here about calculating intersections and designs and all that stuff. So this stuff's going to really help you if you bother to delve into it, okay? And I will be probably doing a quiz, well, another quiz on, I don't know, we probably won't have time to do it Thursday, but I'll probably set it up so that it'll be available on the weekend, okay? So any questions anybody has? Problems, one of the homework problems, or anything you want to look at a vertical curves, horizontal curves, any of this stuff? This lab is kind of just putting everything together. That's what's happening with this. So any questions?
So in the lab sheet that you
Yeah.
showed us,
Yeah, let me pull that up real quick. Let me pull it up. Okay.
and the page that shows us the distance of the road.
Okay, let me get to that. That's this one, I think.
Yes.
Now this one, understand, this actually has both this has got the profile as well as some of the horizontal. So this actually has both on it, okay?
Okay, so typically, because what we were looking at on the actual plans of like other things,
Yep.
we would have to look at the profile for those stations to find that distance and that grade.
Well, not actually, okay? Do you notice here what this is saying? This is saying you're at station 10 plus 00, and this, what does that 61320 mean?
That's the elevation of that station point?
Correct. Now, if you go to that, let me see. All right, let me find this right here. There you go. Do you notice the same thing there?
Oh, yeah, look at that.
See, now, let me tell you something. Not all engineers do this, okay? So this is a wonderful set of plans. I would love to lay this stuff out from this company because they did everything for you. I will tell you, you will get plans from some people. They don't do this for you. So what you have to do is figure all of this kind of stuff out there on your own, okay? So that makes a huge difference. But yeah, that right there is the information, station elevation, and then they've even given you the edge of pavement elevations here. Now, I haven't done that, okay? I haven't done that here. You're gonna do that, all right? So you're gonna have to figure out what station you're at, and then you're gonna have to apply the typical section to get to the back of curve, all right? And do the same thing here. Now, let me ask you this, because I don't have elevations here. Everybody see that? So how are we going to get the elevation of 10, 9, 8, 7, and 6? Who can tell me?
You could start from the elevation of the first point, like 10.
What are you
6.
calling the first point? 10?
Yeah, you can do 10
So
or
where are you
6.
going to get the elevation of 10? I'm listening because I think you're on the right track.
It would be you would follow that that first road, the 37-foot road,
This guy, right?
and then you would, whatever the elevation of the station of the center line would be, you would calculate the curb elevation from looking at typical section, and that'll be your starting point at 10.
Yeah, exactly. So here's what you would do. Notice we're at an 8% grade. See that?
Yeah.
And it's going left to right. So that means this point's lower than that, right?
Yes.
So if we are at 1066.50 out of the center line where it's the same station, so 1066.50 minus 1050 gives me what, 1650?
Yes.
So the distance from here to here is 1650 at 8%. So we would figure out the fall, and then we would subtract that fall from this. That would give me the elevation of the center line. and then I would come over what my typical section's telling me to get that point, okay? You're gonna do the same thing up here. We're at station 4350. We're at a 4% grade. We can figure out centerline elevation. We can figure out back a curb. So if we have back a curb and we have back a curb, what we're gonna do is prorate this, okay? So we're gonna take the difference between this elevation and that elevation, divide it, subtract that difference, divide it by 4, and we're either gonna add that difference, that difference plus that plus the difference, that plus the difference to get it, or we're gonna subtract, okay? So we're gonna prorate this through here. All right, did you get the idea?
Yeah, that makes sense.
Now, I want to tell you, prorating it doesn't always work. Sometimes you'll get an artificial low spot through here, which shouldn't be. So sometimes they have to do that differently. If you go back and look at this Tylersville thing, if you take this elevation here and this elevation here and subtract it and divide it by 4, these aren't exactly prorated. And the reason is because they've got, notice these points out here? They wanted to make sure that the drainage is like coming around this properly. So they warped this a little differently than just prorating it. So it's not always that simple, but we're just gonna do it simply, okay? Does that make sense?
Yeah, that makes sense.
Okay, so use this as a kind of a tool. This is kind of a neat tool. Like I said, a lot of designers, a lot of engineers don't do this. They should, but I've seen plenty of plans where we had to do this stuff ourselves. This right here is a beautiful intersection detail.
So this is not typical.
No, this is not typical at all. Well, okay, let me say this. It might be typical if this was done for ODOT, which it probably is. ODOT probably requires this. So that means whoever the engineer is working for ODOT, they have to provide a document like that. But if you're doing, let's say, a roadway for Hamilton County, they might not have the requirement that you have to do this. So they may give you the typical sections and the profiles and the horizontal geometry and say, yeah, you're on your own when you do the layout. So it just depends on the agency, okay?
Okay.
Yeah, definitely. So we're gonna figure this out because I just wanna show you, it's easy to prorate this stuff. And that's what we're gonna do that's what we're gonna do for our project, okay? So take a look at these, kind of study these so you know what you're looking at before we come in to class and lay this out. So go ahead, you had a question?
I did this really quick. So if that center line location, station 10 plus 6650,
Yeah.
I calculated as a 1.32 feet below 609.2.
Okay, so then you're taking that minus 609.2.
Yes.
So you're saying that the elevation of that point is at 607.88?
Yes.
Yes, that would be the center line elevation, right?
Yeah, but that wouldn't be the curb elevation.
So then we have to come to the typical section for this road, which is a 37-foot road. So let's see what happens there. That's this guy here. Let's see. I think we're using, I can't remember which one I'm telling you to use. It's one of these two here. But you notice it says 4 inches below the center line or 4.5. See that?
Yeah.
So I'm telling you which one of those to use. So we would take 4 inches plus whatever or minus whatever you calculated, and that would get you the elevation.
Okay.
I have to be careful what I'm saying there. I'll tell you what it tells you up here which one we're using.
Yeah, because that's at 18 feet, 6 inches.
We're using the flexible pavement. See that?
Okay.
For the industrial. So that means that we are using flexible pavement. So we're going to be 4 inches below the center line.
Okay.
So you just had what, 607.88, right?
Yes.
And we're going to subtract from that what?
That would be
4 divided by 12.
would be 0.33.
So it's your elevation, your curb is 607.55.
Yeah.
Okay. See how that works then?
Yeah, that makes sense.
So it's not hard. It's tedious, but once you understand it, I mean, there is so much you can do here with these guys. This is a real critical thing that you're learning here. It's real good stuff. And so we're not going to do the grades actually out in the field, but we will set up the grade stakes and we'll put the cuts and we'll get the elevations on the stakes, and then you guys will finish this off. So you'll have time to ask me questions for certain. Okay. But try to print this out, guys, and look at this and read through it so you do have an idea of what we're doing before we get out there so we can roll with this, okay? I think weather's going to be real good for us and this time, so we'll be in good shape. All right? Any questions then? All right. Well, I'm going to go ahead and stop the recording.